expensive.
Yeah, I used to work. Yeah. Eugene Demler as our colloquial expert. Eugene is professor of physics at ETH Zurich. He did his studies at the Moscow Institute of Physics and Technology and received a diploma from the Lebedev Institute of Physics in Moscow before coming to Stanford actually as a PhD student, where he did his PhD in the group of Shousheng Zhang on studies of high PC superconductivity. He went on to become a junior fellow at Harvard, and then after a couple of years became a faculty member and was on the faculty at Harvard for about 20 years before moving to ETH in 2021. In his career, he's been really a pioneer in the field of quantum simulations, particularly of condensed matter physics, using the toolbox of ultra-cold atoms through creative ideas and close collaborations with experimental groups. He's inspired quantum simulations that have shed light on everything from strongly correlated electrons to topological phases of matter to non-equilibrium physics. He also remains interested in real materials, and some of his recent work has advanced understanding of out of equilibrium behaviors of materials driven by light. And for this wide-ranging work, he's received numerous awards, which I won't list them all, but a couple of recent ones are that he was named a Simons Investigator and received the Hamburg Prize for Theoretical Physics in 2021. We're very happy to have him here today to tell us about the pointillist perspective on many quantum physics.
Pleasure to be here. Thank you for the invitation. Thank you, Monica, for this kind introduction. As Monica mentioned, I was a student here, and actually coming to this colloquium was really kind of a major experience in my career. Remember one specific faculty member asking very subtle question to the speaker, why is this important? So we'll see if I get this question at the end of my talk. So I want to begin by acknowledging people who really did all the work that I am presenting, and so special credit should go to my younger collaborators, Fabian and Annabelle, who are young faculty members in LMU, and Ivan Marrera, who is a postdoc with me at ETH. And this work would not be so exciting if we did not have an opportunity to interact with several experimental groups, and I'll show some results along the way, and especially results from the groups, the cold atoms group of Manuel Bloch, Marcus Kreiner, Sim Bakker, and Rudy, and also the solid state group of Attach Imamo. So during the last few years, it has been difficult to escape all the hype around quantum computing. And it's interesting to go back and see how optimistic predictions have been about what it's going to deliver. So there is a so-called Rose's law, who predicted that by the year of 2015, quantum computers will be more powerful than the universe itself. And it actually, more recently, it's still quite optimistically, there was an Evans law who suggested that the computing strength of quantum technology should have double exponential growth, because all the number of qubits will grow exponentially and Hilbert size should grow exponentially in the number of qubits. So you can say that this is a typical Gartner cycle, right? So, and where somewhere near the peak of inflated expectations. And well, hopefully this shock of disillusionment will not be too deep, but then what really matters is what will be left in terms of kind of realistic and productive technologies. And I'll try to advocate today that like the field of quantum simulations is something that is already having impact and will survive through this kind of change of seasons. So we can debate whether quantum computers are really whether there is a kind of strong well, there is a suggestion, but no real proof that quantum computers can solve problems which are intrinsically classical. However, I think everybody agrees that quantum computers have particular advantage when solving problems which are quantum in their nature. And one of the important examples of some of such problems, such class of problems, was suggested by Richard Feynman when he pointed out that if we're facing systems that we cannot solve using standard tools of theoretical physics, we should consider modeling them on a different quantum platform. And probably the simplest example to illustrate this is the idea of high-temperature superconductors, which remain the subject of bitter debate. And when I was a graduate student, it was really kind of the focus of condensed matter theory group. I think the discussion was kind of at the level, well, comparisons were made that, well, we either have, like in condensed matter physics, it's either solving high TC or stem collect. But it's kind of remarkable that in spite of all of the focus, it remains a problem that, you know, we are puzzled by. And this led to the idea to use tools of atomic physics to make an analogous system. So when we talk about in high TC materials, we talk about electrons moving in this complicated structure of copper oxide planes, but for many practical purposes, we can actually reduce it to a simple model of fermions moving in a periodic potential and having local on-site repulsion. We have very different energy scales. In one case, we talk about hundreds of kelvins. In the other case, we talk about sub-microkelvin. But in both cases, we sort of have the same underlying physics, as I'll try to illustrate to you today. It's actually an interesting time to talk about this because okay, we know that the CA is anniversary year for quantum mechanics. It's also anniversary year for the BEC. So this was a picture which probably many of you have seen as an example of Bose-Einstein condensation of alkali earth, of alkali atoms, and roughly the idea is that so there were atoms in a trap, and then if the trap was removed, atoms were allowed to expand, and so like a velocity distribution inside the trap was mapped into real space image. So here we start with the high temperature when actually atoms occupy their high velocity state, and then at low temperatures we see a condensate most of the atoms really being in the same lowest energy state in the trap. But if we look at the history of this field of cold atoms, it's kind of part of the original motivation was that it's a system in a regime which is very convenient for doing theoretical analysis. So distances between atoms were very large and much larger than a typical sketching length. So interactions were weak. One could do simple perturbation theory. And so we could really make predictions which were agreed quite accurately with experimental measurements. But as you can imagine, after working with this beautiful and controlled system for a few years, physicists got bored. And so what happened was that there was a shift towards systems where interactions are large. And one of the ways to make interactions between atoms strong is the idea of the Feshbach resonance. So that goes back to some basic idea of quantum mechanics. Imagine that there is a potential between two atoms which we can control, and as we make attractive potential deeper and deeper, we can think of new bound states appearing in the system. And as the new bound state appears, so here the red line shows the kind of the bound state which starts at zero energy and then goes to more and more deeply bound. The sketching length actually goes through the singularity, and so in particular, see when the bound state is not yet present, we see a sketching length which diverges, And but then when the bound state is present, we see large positive sketching length. You can think about it as kind of second, like from the perspective of second order perturbation theory, two atoms come in and then they virtually go to a state. If that state is high in energy, then like perturbation theory with respect to the higher level lowers the energy, whereas perturbation with respect to the lower energy state, which would be on this side where there is a bound state, if we do perturbation with respect to the low energy state, it lifts the energy up, which describes this positive sketching length, which we naively think of as repulsion. And that was demonstrated in experiments by Wolfgang Ketter's group. Well, but what is closer to what I'll be discussing today is the idea of amplifying interactions using optical lattices. So this was first suggested by Peter Zoller theoretically and collaborators. And some of the first experiments were done in Mark's group. And the argument is that we can simulate, or we can create kind of synthetic periodic potential for atoms by making a standing wave with laser beams. And this suppresses kinetic energy of particles, because now they have to tunnel between the minimum of this potential. And this amplifies interactions because they're forced to sit on top of each other. There are other kind of interesting ways how to make strong interactions within atoms. Many of them pursued here in Mark's, Ben's, Monica's, and John's groups. But that would be like an entire course, which I'm sure is being taught here. So I will focus more on the optical lattice experiments, and I'll be happy to discuss afterwards all these other approaches to getting strong interactions. But like specifically, what I want to focus today is the fermi-Hubbard models of fermions in the lattice. And I'll talk about two cases. One is a square lattice with a connection to in the physics of high temperature superconductors, and the other is fermi-Hubbard model on a triangular lattice. And here there are interesting connections with more rare materials. And I would say that the underlying the real motivation behind what I'm presenting is that if we think about the fields of condensed matter physics and atomic physics, it's not a one-way street. It's not that we just take ideas from condensed matter and just transfer them to the field of cold atoms. But I think we're already getting interesting insights and new ideas from experiments done with cold atoms, which influence how we understand solid state questions. I hope I'll convince you in this. Okay, and I want to emphasize that there was an important milestone achieved experimentally, and this was the development of quantum gas microscopes, which allow to realize these atomic systems in optical lattices with single atom resolution. So what you see here is not a kind of a theorist representation of an interaction from a gas. So this is actually experimental data from one of Bloch's groups. So like where you see a red square, this is a fermion with spin down, blue square is a fermion with spin up, and all, let's say, we have missing sites. So missing atoms, like empty sites. So this kind of reminds us of a style of painting known as Pointillism, where instead of brush strokes, actually masterpieces were created using dots. So what we'll be discussing today is kind of this perspective on many states, which consist of these dots, like individual and measured atoms. And our goal will be to figure out how we can actually learn about the many-body state by analyzing this pointillist representations of many-body systems. Well, so there are kind of couple of basic ideas that I would like to mention right away, which will be crucial to our discussion, and that probably most of you have heard in your introductory in solid state classes, but let me remind you. So imagine that we have say two fermions localized in two potentials. Then, if potentials are deep enough, then we can treat tunneling between the walls as a perturbation. And now we can ask, well, from the point of view of perturbation theory, which configuration is better when the spins are anti-aligned or aligned? Then you can do a simple argument to say, well, if spins are anti-aligned and there is strong repulsion between fermions, I can still consider a virtual process when one of the fermions goes to the neighboring sites, we get a higher energy configuration with a double and a pole, but then one of the fermions comes back. So some kinetic energy can be regained through this virtual process. However, when spins are aligned to the polar principle, tunneling is not possible, and we can capture this kind of tendency of electrons to have opposite spins by writing effective spin-spin interaction. You can see it's positive, meaning that it favors spins pointing in the opposite direction. So it's anti-ferromagnetic Heisenberg interaction. And when doing theoretical calculations, actually, like sometimes I'll present you results which were not obtained on this full Hubbard model in which we are looking at, fermions which move in the lattice, and we have double occupancies which cost energy of U. But we will be analyzing a kind of a simpler version of this, where we say, well, okay, the double occupied states are energetically very costly. We know that they give rise to this anti-ferromagnetic exchange. So let us actually remove this double occupied configuration. So this projection operators say that when fermions move from side to side, they should not create double occupied configuration, but we retain anti-ferromagnetic interactions. So that's the so-called TGA model. Okay, so let me get you oriented where experiments are in the case of square lattices, which is kind of closest representation of the physics of high-density hoop rates. So, okay, like here you can see this is like a schematic phase diagram of superconductors. So what is called doping zero is basically how many sites are missing electrons. So like exactly on this axis, we have one fermion per site, and this is a state which, as we said, because of anti-ferromagnetic interaction between fermions, we have this perfect anti-ferromagnetic order. Of course, like it's perfect. The classical case, quantum mechanically, there will be fluctuations. And then when we start doping, this is where all the debates have been going on for the last few decades. So what's happening? There are very unusual properties of materials. We'll talk about them. So do we have some kind of emergent order, which is either kind of stripes or superconductivity? And until recently, kind of the lowest achievable temperature was of the order of a quarter of the tunneling strength. So here I can show you the results from one of these earlier papers by Marcus's group. So what I measured in this regime, exactly one fermion per site, they see how magnetic correlations change with temperature. And you see these correlations are corrected with the time for the scientists to remove this alternation plus minus plus minus. And at highest temperatures, you see that correlations are very weak and are present over short distances, but then as they lower temperature, they actually get the correlation length, which roughly extends over the system size. But that was still relatively high to see interesting physics. What has happened during the last few months is that Reiner's group actually demonstrated that they can achieve temperature which is like a factor of 5 lower than what was possible before. So we are now in the domain of kind of what we hope to start seeing more of this kind of physics that we're really interested in, including superconductivity. But in most of my talks, I will actually focus on experiments which are done still in this temperature regime. Okay, so let's start with the idea of so why is the physics of doped antiferromagnetic states complicated? So imagine that we start with an antiferromagnetic state. You can see that we have spin up, spin down configurations, and then there is a hole, and then this hole starts to move. And as it moves, it actually kind of creates unfavorable configuration of spins. And the more the hole propagates, you see this kind of chain of frustrated spins left behind. And this actually suggests that we can think of the point where the hole started its motion as one kind of object, whereas the point where the hole is another object, and then these two objects are connected by a string. They are typically called a spin and a column. So in one dimension, one can show that there's a true separation. The spin and the column can move freely away from each other. Whereas in 2D, they can separate by finite distance, but they're not really, but they cannot liberate, they cannot propagate separately. And this reminds us very strongly of the picture of mesons in QCD, which consists of quarks. So they're bound together by a linear potential. It's kind of interesting that this idea was suggested maybe for the first time, at least I learned it for the first time when I was a PhD student here, and Bob was quite excited about this, and this was developed by other people. And I will not have time to go through the details, but I think we actually have very strong evidence from this kind of new generation of experiments and quantum simulators that this picture is good in even in quantitative description of what's happening in this whole models. But let us look at the data. So in this experiments from Emmanuel's group, so they started again, as we said, anti-ferromagnetic state, and they introduced one dopant. In their case, it was a doublet rather than a hole. But for the Hubbard model, it turns out that it doesn't matter. One can prove rigorously that whatever is happening to a hole will also happen to a doublet. So this doublet is free to move anywhere in the system. But what we want to understand is how this moving doublet changes magnetic correlation. So what is plotted here, what's being measured is spin correlations relative to the position of the doublet. So they always put the doublet in the center of the image. It doesn't mean that the doublet was confined here in the center. It's just like it could be anywhere, but the position is always, but spin correlations are shown relative to the doublet. Here you can see color coding of nearest neighbor correlations. So if you think about it, this is already a 3-point correlation, like it shows correlation between two spins, but as a function of distance to the doublet. So like all of our traditional many-body physics is based on 2-point correlations, whereas here, what is being measured is a 3-point correlation function. So it's a new way of studying many-body states. Well, in the case of this nearest neighbor correlations, you can see that they change quantitatively, but they at least have the same character. They are more anti-ferromagnetic, the larger magnet goes away from the doublet, and they're suppressed near the doublet. But at least the important message that we get is that suppression of anti-ferromagnetism is very local in nature. It's really next to the doublet rather than the system as a whole. And then if we look at diagonal correlations, then the effect of doublet is even more striking. So if we look far away from the doublet, relations are ferromagnetically. Just think about if we look at diagonal, you can see that if you look at the picture of anti-ferromagnet, then spins which are on the diagonal, they are aligned the same way, so the ferromagnetic and corresponds to kind of red color coding. But diagonal correlations which are next to the doublet, they have the opposite sign, so they're anti-ferromagnetic. So how can we understand this? Well, think about this situation when we start with a hole right in an anti-ferromagnetic state, and let's say look at these two fermions. Well, they originate from anti-ferromagnet, the nearest neighbor, so they're anti-ferromagnetically correlated. But when the hole moves, now these two fermions find themselves on the diagonal. So now when we look at diagonal correlations next to the hole, right, we have some of the correlations which sort of originate from the original anti-ferromagnetic state, and some correlations which used to be nearest neighbor now became next nearest neighbor, and that's why they're anti-ferromagnetic. And so when we measure force which is average over all of them, and nearest neighbor correlation was stronger. And that's how we end up with diagonal correlations becoming actually anti-ferromagnetic rather than ferromagnetic. And one can actually turn the picture, this kind of meson-like picture of magnetic polarons that I told you about, into a calculation. And roughly it works the following way. So, like as a simplest starting point, we can assume that the spin doesn't move. In reality, it can move with super exchange and what we can put it in, but it doesn't change the result so much. But primarily what's happening is that the hole can propagate much faster. But as the hole propagates, it leaves behind these spins. Now, if we want to label the state of the system, it's not enough for us to just specify where the hole is at any given time, because depending on which trajectory the hole chose, it actually leaves behind different types of strings. So, and that's why we can label possible configuration in this kind of, technically it's called beta lattice, but every side on this lattice just corresponds to a different trajectory. So we have like hopping of the hole on the strange lattice with a linear potential. So it's sufficiently simple problem to solve. We can solve it, and then we realize that as the hole moves on this lattice, once we know its wave function, well, we can learn what kind of reshuffling of the spins has been done. And from that, we can compute what we expect to be a change in spin correlations, which is what has been done here. So there is, let's just look at the green line. So this is basically similar data to what we discussed before. So there is a doubling, and this is nearest neighbor correlations as a function of distance to the doubling. So these experiments, and we see that these correlations remain anti-ferromagnetic with decay, and this is this geometrical string model. On the other hand, if we look at diagonal correlations, then experiments we already saw that they change sign from being ferromagnetic away from the doubling to being anti-ferromagnetic close to the doubling, and this is this calculation based on this geometrical string model. In fact, one can do even further. So this is what was done in Marcus's group. So one can ask a question: as a hole propagates, it leaves behind like strings. Can we actually see strings in the data? After all, by getting the snapshots, right? We know what every particles are, and so that's exactly what they have measured. So that there is like lower line shows distribution function of strings without doping, it just responds to quantum fluctuations in the magnet, and there is dramatic increase in the number of long strings when there is doping. Notice it's logarithmic scale, so the increase is almost a factor of 10, which shows that moving holes actually do introduce many of the strings. So here you can see that we're actually, from these pictures, we're actually getting patterns, like distribution of strings. Okay, but of course, what we want to do is study physics beyond a single polaron, and we want to see how many body states emerge. And here, as a reference, I'll show these results from the access group. So they, for different types of measurement, they of course like summarized it using the ARPAS. They measured ARPAS data, but interestingly, many of these measurements indicate the same physics. That we go back to the phase diagram, and so it's phase diagram doping versus temperature, and we ask like how does the nature of Jose particles change for different doping levels, and what one expects in traditional metals. That if one goes to lower temperature, one gets better and better defined Jose particles. So that's a special measure of what they measure in ARPAS, like how well Jose particles are defined. And so for strong doping, they see exactly this kind of fermi-liquid-like behavior. But for small doping, on the other hand, this Jose particle becomes worse and worse defined. So it's clearly the behavior which is the opposite to what we expect in metal. And this difference, there is a kind of across certain doping where behavior changes from more from liquid-like to this more exotic-like, called the pseudo-M. Well, what I'll try to argue that if we look at results coming that have come from quantum gas microscopes, we can make the case that there is this crossover, and we can think about it from the liquid of polarons, which we just discussed, to more traditional fermi-liquid, how we understand interacting fermions from using perturbation. So again, there have been many experimental measurements done in this case by the group of Emmanuel Bloch. Let me focus on just a few. So what they measure is spin correlation function. So this is, in this case, just they're looking at diagonal correlations as a function of doping. And what you see is that close to 1 fermion per site, that's was our antiferromagnetic mode insulate. On the diagonal, we expect to see ferromagnetic correlation. Indeed, this correlation starts being ferromagnetic. But then with larger doping, they change and they become antiferromagnetic at longer distances. Then they take kind of sites which are separated by 2 lattice constants, but still they're chosen in such a way that in the antiferromagnetic mode state, they would be ferromagnetically correlated with each other. And then they start changing doping, and they see that this correlation, which used to be ferromagnetic with doping, changed to antiferromagnetic. So then even longer range correlations, but such that they're ferromagnetic at half filling, but with doping, they become antiferromagnetic. And this all happens at roughly 1 filling of around around 30%. And in fact, antiferromagnetic correlation is something that we would expect based on the theory of simple metals, right? It's just like Pauli principle that if we have weakly interacting fermions, while we cannot find 2 fermions with the same spin on the same site, although we can do so for fermions with opposite sign, that's why we're more likely to find fermions with the opposite sign next to each other. So we find that sort of with doping, at least large doping is indeed consistent with our expectation of what kind of spin correlation should look like. And whereas at small doping, it's actually more it's more reminiscent of what we find in mode insulator. One can then do Fourier transform of the spin correlations. And so close to half filling, one finds a peak at pi. That's the signature of antiferromagnetic order. Whereas for strongly doped systems, one finds 4 peaks. That's something that one would find by doing like simple perturbation figure, like RPA. It's a way of resumming interactions. So, and again, to change from like the mod-like behavior of relations to something we would expect from our something that I learned from Sandy Fetter's book when I was a student here. It all happens around 30% doping. And then one can look at even like a more sophisticated correlation function. This is a 3-point correlation function. Again, it's like spin as a function of distance to the pole. Let me not go through all of the details, but just want to emphasize. So these are experimental results as a function of doping, but then we can compare them to different theories. And there is one theory which we already discussed. This is a geometrical string, and we see that it actually kind of it's not so bad at small doping, like close to half filling. And particularly it shows the change of sign, but then it doesn't work for larger. On the other hand, we can take theoretical models which are more kind of in line with traditional treatment like RPA or like even RPP. But what's common for these traditional theories, they assume that as holes moves, they frustrate, they sort of modify spin correlations on the average. It's not a local picture of spin configuration being distorted in the vicinity of the hole, but really on the average. So these kind of averaged approaches, they actually work quite well for strong doping, but they fail when we talk about weakly doped regime. In particular, they don't even show the change of sign correlations. So we clearly see that this microscopic model based on local picture of spin correlations modified in the vicinity of holes works at small doping, whereas at larger doping, we go to the regime where traditional kind of condensed matter mean field type approaches work. So I think this is sort of, it's very suggestive that the way to understand the crossover which we saw for pursuing cuprates, that like for weaker doping, we should talk about polaronic fluids, whereas at larger doping, the system goes to a more liquid-like behavior. Yes.
Just a question on the So should I like actually draw anything meaningful from the fact that like the ED isn't matching well at Delphi large doping, or is that just experimental noise?
It is exactly like it just shows that yes, it is honest.
Just some experimental noise. It's just some experimental noise or difference between.
But it's fact, yeah, it's finite size. Like with ED, you can only do 4x4. In experiments, they had 10x10. But that's the limitation of ED. You cannot do larger systems. Good, yeah, please feel free to interrupt.
So is there a transition from the strange matter to the Fermi liquid?
In this case, no, it's a crossover. So it's more like which perspective is better for describing like what you see in the snapshots. Okay, but obviously the question you can ask, well, can we see Hall pairing, especially because that's really the quest which is driving a lot of kind of quantum simulation, and especially in this kind of older generation of experiments before the new one, when temperature was only a quarter of tunneling, it seemed like temperature was too high. Well, but I want to show you that the unique toolbox of cold atoms allow to overcome this. And it actually has an interesting prehistory. So when theorists started thinking deeply about physics of the Fermi-Hubbard model, realized that it's so hard to do any accurate statements about it in the case of 2D, they wanted some intermediate models which has complexity, richness, not necessarily complexity, richness of the kind of 2D Hubbard model, but easier to solve. And so that's why they got interested in tool-like systems. And I believe kind of Maurice Rice was one of the first to think about it. And in particular, the idea that Maurice Rice and then also Heinz Schultz advocated was as follows. Let's imagine this Fermi-Hubbard model on a ladder. Then we know that we have antiferromagnetic interaction, so it's actually good to take these neighboring spins and bind them into singlets, right? And now if we dope it, well, then holes will go into the same bonds because this way they introduce minimal frustration to the singlet. Okay, well, looks like a reasonable argument, but except that you realize it's actually somewhat suspicious because it's true that we can save on this exchange energy between the chains. However, the penalty that we will pay is that now these holes cannot move independently from each other. So we gain on the energy, on the super exchange energy, but we lose on the energy of the perf, of tunneling. And actually, J, we introduced as kind of high order correction, like in perturbation theory in tunneling. So it's not obvious, therefore, that the gain in exchange should overcome kind of the loss of the kind of increase in energy in P perp. Well, but you know, for theorists like it's easy, they can always just make this J perp larger than T perp, right? So then what Maurice and collaborators have done, they said, oh, okay, let's say this is what our J perp should be if we start with an honest Fermi-Hubbard model. But let us just make J perp larger. To make J perp larger, this will of course boost the energy gain due to pairing, and indeed they can immediately they identify very strong, strongly bound holes. And well, then they showed that in principle pairing survives even like for realistic J-perp. However, binding energy becomes very small, so kind of even modest temperature would suppress that. Okay, well, so what I want to show you is that actually something that looks like a Gedanken experiment can actually be done in the lab. And so the trick was to actually apply a bias between the chains. So what happens, what this bias does, right, it actually, if we make bias sufficiently strong, then actually the process of moving a fermion from one chain to another is like so far detuned in energy that effectively it's switched off. On the other hand, now if we think about this kind of virtual tunneling impact, the energy of the intermediate state is no longer this repulsive energy U, but U minus delta. And that's why having this bias actually makes the exchange interaction larger. Therefore, this approach actually achieves two things. It switches off single particle tunneling T-probe and it boosts J-probe, which is exactly what Morris Rice and company wanted to do in their model. Well, and that's exactly what was done in the group in Munich. So what you see here is a picture of basically a snapshot of fermions in a ladder. You can clearly see two holes on the same run. Of course, okay, you can say it's a single image. We should do a real kind of study. So here, what is plotted is probability to find two holes, like in the two chains, as a function of distance between them. And so, if we take plain vanilla ladder, then actually we're less likely to find two holes on the same run. So in this regime of temperatures, actually, some call this kinetic energy is dominant, and therefore we do not get binding. On the other hand, when this kind of imbalance is added, which makes exchange interaction strong, then we immediately find like a large kind of increase of the probability of finding two holes on the same run. So we find very strong hole bunching. And it's entirely driven in this case by magnetic energy, because we're dealing with a regime of strong this J-probe. And so if we start with a configuration of strong singlets, but now the holes separate, then clearly our singlets are no longer benefiting from the exchange energy. So that's kind of a direct example of binding driven by magnetic interaction. Well, okay, and then if they add more holes, they can see that these pairs can start behaving as bosons with repulsive interaction on the ladder. They try to stay away from each other. And of course, like the question is, so what happens if we go to the larger system size to go beyond the ladder? So that's actually kind of the most recent work that they created not a single kind of this. The systems are called mixed dimensional because you see what is done in experiments, right? We switch off single particle tunneling. So tunneling is really happening along the chain. So from the point of view of tunneling, it is one dimensional. But from the point of view of super exchange interaction, it is two dimensional. And so here, like they created basically, it's a collection. You see that there is like this bias between different wells, this one and that one. And what they saw is that whereas for one ladder there was like a pair that was found, but now this kind of holes start aligning up, and so we get a picture of what's known as strike physics, something that I mentioned before. Again, you can see it in the correlation function. So in you can see it in blue color corresponds that along the chains, actually holes are trying to stay away from each other. Whereas this red color means that there is actually bunching in the vertical direction. This mixed dimensional direction, actually holes are trying to line up with the string. And that, of course, is a kind of the type of physics which is very dear to the heart of Steve and Tom. So now there is a new playground for exploring this. Okay, so far we focused on the square Hubbard model, but in the last few years, of course, there was a lot of excitement about electron systems in triangular lattices driven by Moiré, with a lot of interesting physics, superconductivity, magnetism. And this is also where experiments have made a lot of progress realizing triangular lattices. In fact, one can even go continuously from a lattice which is, let's say, by prime switched off, then one goes back to a square lattice, and when it's equal to T, then one gets a triangular lattice. Okay, and so actually magnetism in triangular lattices has been a subject of a lot of interest to commencement of theories. There have been many suggestions, and one of the new features is that when interaction is weak, then one doesn't even find magnetic order, that there is not even insulating behavior. It's a metal, then there is phase suggested by Bob Laughlin quite some time ago, and only at very large interaction we go back to this antiferromagnetic type Heisenberg picture in which spins align with this 120-degree pattern. So it's very interesting physics to explore. But let us look what has been seen in at least one class of materials, Moiré materials, which is transition metal dichology. So these experiments are from the Cornell group, and what is shown here is spin susceptibility as a function of doping. The way it's measured also shows an interesting connection between cold atoms and condensed matter physics. So I'll not explain it now, but if at the end people will ask me, I'll be happy to explain why. Just even the way it's an optical measurement, which was kind of had a lot of influence of cold atoms when it was developed. But let's go back to just the results for spin susceptibility. So the way they present the spin susceptibility is a way one would present spin susceptibility for kind of lattice models. And what's important is this parameter theta. So if theta is equal to 0, we have spin susceptibility, which is 1 over t, which are just free spins, like non-interacting spins. When theta is positive, then we have basically enhancement of susceptibility, which indicates ferromagnetic interactions. And if theta is negative and we get suppression of spin susceptibility, this indicates antiferromagnetic interactions. So essentially within the error bar, they find, and what is plotted, this red color is minus theta, right? And so what you can see is that exactly at 1 fermion per site indicates corresponds to 0.5. Within the experimental accuracy, like spins behave as if they're non-interacting spins. That's very counterintuitive. Remember, for in the case of square lattices, that the strongest magnetism is exactly for 1 fermion per site. Here, it's as if there are no magnetic interactions. There is 1 fermion per site. Then, when they do, in one case, they get antiferromagnetism. In the other case, they get ferromagnetism. So somehow magnetic interaction is switched on by doping, which is the opposite of what we saw in the case of square lattices, where magnetism gets suppressed by doping. Here, it only appears because of doping. And even more surprisingly, it changes sign depending on how we dope. And then similar experiments were done in the group of my colleague, Atachi Momoglu. So they do not see antiferromagnetic correlations on the cold dope side, but they see very strong ferromagnetic correlations on the double dope side. And they also see that there are no interactions. Effectively, we have decoupled spins exactly at half billion. So very kind of distinct behavior from what we saw in the case of square lattices. Okay, so I want to explain what is the new different type of magnetism that has been seen here. And okay, maybe I can use this as an excuse to somewhat complain. So we wrote a paper about this quite some time ago, and it had been fighting for 3 years. And the reason was in the same paper, we said this will apply to both cold atoms and solid state systems. And the referee just refused to accept this. He said, no way. You just talk about one. And only after, there were basically experiments with both, I showed you solid state experiments and then cold atoms experiment. Then only that changed the mind of the editor to accept the paper. So it was a long fight. Anyway, actually the history of kinetic magnetism goes back to Nagaoka, and his argument was kind of curious, so let me take you through. It was done in the context of the square lattice. So he said, well, okay, we just talked about antiferromagnetic interaction. So if we have 1 fermion per side, spins align antiferromagnetically. Every pair of spins gains energy t squared over u, and there are n spins in the system. Now imagine that we put one hole, and then actually we ask, well, what is best kind of background for the hole to propagate? And actually, it's good. It's best when all spins are aligned, because now, regardless of how the different trajectories of how the hole moves, they all interfere constructively. So that really lowers kinetic energy of the hole. And so in the ferromagnetic case, lowering of the energy is T. And now it becomes an interesting order of limits question. So what Nagaoka did, he said, let us first send interaction to infinity. When we send interaction to infinity for a finite number of sites, we switch off the exchange. And therefore, now that in this case, always ferromagnetic state will be favored. And now we can send into infinity, well, because it's true for any n. Okay, so the second idea which I want to introduce in this context is the idea of frustration. So it's something that probably most of you remember for triangular lattices from this example of the anti-ferromagnetic interactions on a triangle. So we can put two spins in such a way that the interaction is optimized between the two of them, but then we don't know which way to put the third spin. Well, so do we actually need okay, but it's not the only way to get frustration. Actually, if we go back to even simple example of electrons moving in a magnetic field, there is also frustration. So think about like a lattice system and particle moving like a single, like a placket. And then obviously to get from one corner to another, particle can go on the upper trajectory or on the lower trajectory. And this trajectory, like contributions to this amplitudes come with phases, and the differences in phases is exactly the magnetic flux through the placket. And so if this flux is large, particularly is close to pi, we can get very strong destructive interference. And that's actually like the idea of why we get kind of this flat Landau level in the quantum Hall effect, or effectively kinetic energy is suppressed because different ways of particle moving, they all interfere destructively. But do we need magnetic field in order to get frustration? Well, let me show you that there is actually an example which is relatively simple without a magnetic field. Let's consider a triangle. And now let's start with like a spin polarized system and introduce one hole and ask, well, let's look at the motion of the hole. First of all, we want to then change the system from hopping of electrons to hopping of the hole, because we have just one hole. But this, of course, exchanges operation annihilation operators. Now, if we want to put back the hole in this operator for the hole into the right order, we see that we acquire a minus sign. So for the hole, actually, like as we make the transformation, hopping changes sign. And on the triangular lattice, this has a dramatic effect, because to go from, let's say, this side to that side for a lower trajectory, we do this single hopping with the negative sign once, but to go on the upper trajectory, we do two hoppings like with a negative sign, and like so product of two negative numbers is a positive number. Therefore, contributions of the upper path and lower path, they actually differ in phase by pi, and there is destructive interference. And you can see this also just by looking at dispersion of a single hole. And usually in the tight binding model, the bottom of the band is at kind of minus t times the number of nearest neighbor. Here there are 4 nearest neighbor, we would expect it at -4. But in fact, it's actually only -2. And that's exactly because of this frustration for the hole in the fermionic system. Let's say in bosonic system, actually, this doesn't happen, because for bosons, we do not get a minus sign, right, when we exchange creation annihilate. We create two creation annihilation operators. And well, actually, this, okay, it seems like a formal exercise, but Christian Battista some time ago pointed out that this gives rise to a very interesting mechanism for anti-ferromagnetic interaction. He said, well, let us consider a hole in the presence of now spins which are actually pointing in the opposite direction. Because now if we do the same exercise, like look at a hole which moves this way, or a hole moves on the upper trajectory, what's left behind is distinct configurations of the spin. And therefore, we don't have to add them, and they no longer add up with opposite signs. There is no destructive interference. So it's actually energetically favorable to have a hole surrounded by opposite spins rather than the same spin. So there is a bound state. And actually this binding is quite dramatic. its energy is set by tunneling rather than super exchange. And that's actually why, let's say, we got interested in this in the context of cold atoms, because that shows that you can get binding set by very different and magnetism state set by very different energy scale. And this is actually kind of a related argument was given earlier by Carter and Shastri when they analyzed U equals infinity limit for triangle, that is sort of in contrast to Nagaoka's regime, and they found that the lowest energy state is corresponds to the configuration we would find for anti-ferromagnetic interaction when spins make this 120 structure. Well, okay, so then you can ask, so okay, if it's all kinetic, if it all arises from kinetic energy, let's look at a simpler model. Let's look at the regime of U over T going to infinity. And in fact, like in the case of more systems, if we look at the relevant experimental regime, then the interaction scale can be as large as 200, 150. So it's not such an unphysical regime to analyze. So clearly, in this case, when U is so large, our super exchange, which is T squared over U, is essentially zero. So there is no super exchange mechanism to speak of as we're used to. However, we still have this kinetic mechanism. So we know that the hole will favor anti-ferromagnetic spin configuration around itself. But in the case of the doublet, we don't have to do particle-hole transformation. Actually, we will favor ferromagnetic configuration. And indeed, if you do theoretical calculations, you find that if we look at this 3-point correlation function, which we discussed in the case of quantum gas microscope, so it's like dopant, which is either hole or a doublet times spins. In the case of holes, they develop anti-ferromagnetic correlations. Notice like very high energy scale. It's set by tunnel. That's when the exchange is equal to zero. And in the case of doublets, we see ferromagnetic correlations. And then we can also take this model, right, in the regime of interaction going to infinity and ask what does it mean for spin susceptibility. We can parameterize it the same way as we saw results in Parnell group in terms of this theta. And since we're working in the regime where effectively the super exchange is zero, exactly at half filling, we see free spins, so no interactions. And then if we double dope, we get ferromagnetic interactions. And if we hold dope, we see anti-ferromagnetic interaction, just like was seen in experiments. And okay, of course, like you also want to see this in like these correlations in the real world, not just like on a computer. And this is what was done in Wasim's group. So they analyzed, they basically looked at exactly this correlation function, right? A whole spin. And in this case, they chose, and you can see that it actually, they get like very strong anti-ferromagnetic correlation right next to the hole. But when they switched the dopant to a doublet instead of anti-ferromagnetic correlation, they saw ferromagnetic correlations emerging. And this was also was done in parallel with the work in Greiner's group, where they analyzed these doublet spin-spin correlations. But now as a function of interaction, you can see that for modest interaction, let's say far from the doublet, they still see anti-ferromagnetic correlations. And then there is a little bit of ferromagnetic correlation in the vicinity of the doublet. But as interaction U gets larger and larger, so the super exchange disappears, and what we're left with is just a large ferromagnetic polar. Okay, so like here we can actually see this ferromagnetism as it arises like real space images. And okay, maybe I'll just take 2 more minutes to point out that another evidence for this picture of magnetic polars that came from the Carnot group, it actually followed the theoretical expectation that if we take, like again, let's go back to our triangular lattice. Like imagine that we start with a large magnetic field. but all the spins are polarized. And now we start lowering magnetic field. What will happen? Well, we realize that, well, it's actually good for the hole to bind, to have an opposite spin next to it, because then it actually, we know that it lowers the kinetic energy of the hole. So then what we expect from magnetization, instead of decreasing smoothly, it actually will decrease in plateau in the step-like fashion, because it sort of basically will happen by a hole binding one spin at a time. And this only happens on the hole doped side. Well, that's exactly what has been seen in the Cornell group, where on the hole doped side, when they look at magnetization as a function of magnetic field, they see it's very pronounced plateaus. However, these plateaus are absent on the double doped side. And actually, okay, just recently, first to say, I didn't know about beautiful work in Ben's group, which also saw this physics. Okay, so with this, let me conclude. I try to give you a kind of like at least a few snapshots of the type of information which I think is very complementary that we're getting from mathematical experiments and from experiments with quantum gas microscopes. I think that say like some of the questions which are raised in the context of solid state physics are already being answered by experiments with cold atoms. Thank you.
Great.